Okay, so in the last class we started this topic acoustic emission testing, and we have learned about the basic principle wherein we saw it is primarily due to the elastic waves, elastic stress waves, which are generated inside a component when it is loaded. We listen to those waves which are coming out from the part through a sensor. Okay. So, when a part is loaded, if you have a defect which is active, for example, if you have a crack which propagates when it is loaded, then it will generate these stress waves which will come out as sound waves from the sample. And now, if you have a sensor which can receive these waves and convert them into an electrical signal, you could get a defect signal, and that is how you get the indications about the defects in this particular technique. Okay. And then we also saw the sources of acoustic emission in different kind of systems, and then finally, we learned about the typical nature and characteristics of acoustic emission. Okay. So, in today's class, we are going to see what are these source parameters, what kind of system you have, and how it is used to do NDT. Okay. So, let us first take an example of a source in a given system, and then see what are those parameters which control the emission events in a particular system. For a particular kind of defect. Okay. Let us say we are talking about this initiation and propagation of a crack. So, this is one of the major sources of acoustic emission, as we have seen in the last class. And let us say we are talking about mode 1 type of loading, in which case you may know that if this is the crack, the loading direction is perpendicular, okay, like this. So, in this case the relationship between the crack size and the acoustic emission will be given by an equation like this. So, let us say this is the stress sigma, so the relationship between the stress and crack size, let us say crack radius is A, and the detectable A signal. The relationship between these three parameters will be given by this equation. This will be in terms of watts. So, we are talking about the signal strength, which depends on the stress which is being applied, the size of the crack, and V is the velocity of radial velocity of crack propagation. So, if you remember, I had said before that the crack has to propagate in order to generate acoustic emission events. So, this is the V is the radial velocity of crack propagation, and on the right hand side you have two parameters. One is H, which is the distance between the source and the receiver, So, this is the source to sensor distance, and x is the smallest displacement that the sensor can sense. Okay, so, these are the different parameters which control acoustic emission from crack propagation. And therefore, these three parameters sigma, A and B are called source parameters. For an acoustic emission event coming out due to initiation and propagation of cracks. We will take another example of acoustic emission event due to a different reason. So, let us talk about a metallic system, and let us say it is a system in which you have a phase transformation. Okay. So, as I have told before, this kind of events in a metallic system can also lead to stresses, and due to which acoustic emission events can generate. Okay. So, let us talk about an A source from phase transformation. You might have heard of martensite in steels. So, it transforms from a high temperature phase called austenite. Okay. When you heat it and then quench it fast in liquid like water, then that high temperature phase transforms to martensite. Okay. And these two phases are very different from each other in terms of their structure and properties. And since they have different kind of structures, the volume of the parent phase and the transformed phase are different, and due to that some stresses can be generated which may lead to acoustic emission. Okay. So, that is how it happens in this case. So, let us say we are talking about this particular transformation, austenite to martensite. So, as I said, this will be accompanied by a volume change also. Okay. So, the stress due to this volume change if we call that as delta sigma, will depend on these parameters. Let me first write it and then I will explain these parameters. So, in this case I is an identity matrix for example, it could be an n by n square matrix. C is the stiffness tensor of the parent phase, and therefore, C plus delta C is the stiffness tensor of the product phase. That means, delta C is the change in that stiffness due to this phase transformation from one material to another material. Beta star, this is a parameter known as unconstrained shape change. And this is the stress beta naught, which could be a pre-existing stress or could be residual strain. Okay. D is known as a shape matrix and V is the volume of the transformed phase. Okay, so these are the different parameters which control the acoustic emission from an event like phase transformation. Let us simplify a bit so that we can get a direct correlation between the stress which is developed due to it and the parameters related to the phase transformation. So, if you say that the change in the stiffness delta C is much lower than C and there is no residual strain, that means beta naught is 0, then this will simplify to this. Okay. So, here you can see the change in the stress which is directly related to the intensity of the acoustic emissions which will come out due to this phase transformation event. This is directly proportional to the shape change which is this. So, it depends on the shape change, because that is what is going to introduce the stress when it will try and accommodate this change. Okay. And it also depends on the volume of the transform phase. Right. So, these are the two main parameters related to the phase transformation as such, because C is a constant which is a material property. As far as the phase transformation event is concerned, these are the two things which will come due to that transformation. One is the shape change, because it is going from one material to another material, and other is the volume change for the same reason. Okay. So, these two parameters will control the intensity or the level of acoustic emission from a phase transformation event in metallic systems. So, these are two examples just to let you know that what kind of event can lead to what kind of acoustic emission intensity, and what are those parameters which will control that intensity. Now, we are going to talk about the characteristics of the A signal, we have seen the sources and some of the typical properties of acoustic emissions. Now, if you talk about a particular signal coming out from a particular acoustic emission event, then it will have certain characteristics, certain properties. So, let us go ahead and see them. Okay. This kind of AE signals they cover wide range of energy level depending on what kind of source you have, how big is the source, and so on. And frequencies. So, it could have different frequencies also, because these are coming out like sound waves. So, they will have different frequencies depending on the source. And there are two basic types. So, this can be classified into two types. One is known as continuous type. So, these are the signals which are sustained signal coming from rapidly occurring sources. And second type is burst type. So, in this case you will see in the continuous emission waves, suddenly you will see some bursts like this. So, burst type is signal bursts in a field of continuous emission. And this kind of signal come from individual emission events. Okay, so these are the two types of signals depending on what kind of source you have. So, the other properties of these emissions the radiation pattern is same as ultrasonic waves, which we have talked about before. And they radiate energy in all direction. But sometime can become directional also, that means it can grow in a particular direction preferentially. For example, if you have a crack of sufficient length, it can become directional. So, any wave it has its own wave form and wave pattern, in which you talk about a central frequency and a variation across that frequency. Okay. So, you can either say it is a broadband or it is a narrow band wave, okay, depending on whether that variation about the central frequency is larger or smaller. Okay. So, acoustic emission waves that you have they are generally broadband, and the received frequencies cover a wide range from audible to (400 kilohertz or higher). Okay, so this was about the signal properties or the characteristics of the signal coming out from acoustic emission events. Okay. So, before we close today, let us take a moment to summarize today's lecture. In today's lecture, we saw these two sources as an example of acoustic emission source. One was from a crack which is propagating, and in this case we learned about these source parameters with regard to a propagating crack, and these were primarily the applied stress, the crack radius, and the radial velocity of the crack propagation v. And the other source that we talked about was from a phase transformation event in a metallic system. And in this case we talked about this phase transformation from austenite to martensite. And we saw in that case, due to a change in the volume and the shape, when you transform austenite to martensite, due to that change there is some stress which is developed inside the material, and due to that you have acoustic emissions. Then we talked about the type of signals, type of acoustic emission signals, and in this we saw that there are two types of signals. One is continuous, and the other one is burst type. So, these are the two types of acoustic emission signal that generally come out from samples which are being loaded and in which you have active defects. Then we also talked about the signal characteristics, of acoustic emission signal, and there we saw what is the typical nature or typical character of an acoustic emission signal, which is coming out from a sample due to some dynamic events like crack propagation and all those sources that we talked about before. And with that we come to the end of this class today. So, this is all I will have for today, and the rest of the things that we have for this particular technique we are going to discuss in the next class. So, for today I will stop here. Thank you for your attention.